All right, this is 2007 and for Q number 5. So this says the volume of spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function, r of t time, where t is measured in minutes. All right, so remember your units, but it's up here anyway. For t between 0 to 12 seconds, the graph of r is concaving down. So this is kind of important for us later on. The table above gives selected value of the rate of change, r prime of t, of the radius of the balloon over the interval between 0 to 12 minutes. The radius of the balloon is 30 feet when t equals 5. So this is going to be helpful, right? So now, note, they give you the formula for volume of a sphere, and that comes in handy. Estimate the radius of the balloon when t equals 5.4 minutes using a tangent line approximation at t equals 5. So this is the one where we did linearization, but if you don't remember that, just remember, use the tangent line, right? So what does tangent line need? Tangent line needs the slope, it needs the values, x and y values. So at t equals 5, part A, at t equals 5, what is my balloon? We are at 30 feet. So the balloon, the radius is 30 feet, r equals 30, all right? So I already have the x and y value. I need the derivative, so r prime of 5. So what is the derivative at 5? Well, the speed at 5 is right here, it's 2.0. So that's my slope. So my linearization, my L of t, right, or y equals, so you have your slope times your x minus x1, so t minus x1, and then minus or plus your y1. Because we used to do it as y minus y1 equals m times x minus x1. So this is just a little cleaner way to write it, right? So you could clean that up, or at this point, since you already have your function, you could go ahead and plug in your 5.4, because that's what you're trying to estimate. You're trying to use this to estimate the value at that point, since I don't have it up here. So L of 5.4 is equal to 2 times 5.4 minus 5 plus 30. That gives you 2 times 0.4 plus 30. That is 0.8 plus 30, so 30.8, right? So what does that tell me? That tells me that the radius is about 30.8. Radius is feet. So this is my radius. Okay. So is your estimate greater than or less than the true value? Give a reason for your answer. So remember what it says. It says that throughout this graph, at least the ones that we care about, it is concaving down. A graph that is concaving down is this way. Your tangent, no matter how you draw it, notice how my tangent is always above my line. So this tangent is always going to be an overestimate. So that's how you give a reason for your answer. Because it's concaving down, the tangent is always overestimate. Is greater than the actual value. All right, so, okay, that's it for part A. Part B then says, find the rate of change of the volume of the balloon with respect to time when t equals 5. Indicate the units of measure. So we're trying to find a rate of change, which is, we're looking for dv dt, right? So we have our function of volume equals 4/3 pi r cubed. So dv dt, because it's looking for the rate of change of balloon, so the volume of the balloon, changing the balloon volume, is equal to 4/3 times 3, that's 4 pi r squared dr dt, right? And it says when t equals 5. Well, at t equals 5, we know that the radius is 30. And we know that dr dt from here and from the chart is 2.0. So 4 pi times 30 squared times 2 would give us 7,200 pi feet cubed per minute, because this is a change in volume per time. So feet cubed per minute. And that's it for part B. All right, part C. Use a right Riemann sum with the 5 intervals indicated by the data in the table to approximate the total feet that has been traveled, so total feet in changes, total feet in change in the 12 minutes. So using correct units, explain the meaning. So this is a change in radius in feet from 0 to 12 minutes. So how do I use a right Riemann sum? Right Riemann sum, remember, is when you don't use the first value. So if you go back to your table up here, that means I'm going to use all the y values except the first one. What you need to be careful about is the intervals are not the same. So your height, actually your width, is not going to be the same. So in the first interval between 0 to 2, that is a difference of 2 times the height of 4.0, plus the next interval between 2 to 5, sorry, let me move this down, between 2 to 5, that's a difference of 3 times the height of 2. Next interval between 5 to 7, that's an interval of 2 times the height of 1.2. And the next interval, 7 to 11, that is a difference of 4 times the height of 6. And lastly, between 11 and 12, that's a difference of 1 times 0.5. If you add it all together, do your calculation, that's 13.9 feet. So the integral between 0 to 12 of r prime of t is the change, right, in radius in feet from 0 to 12 minutes, and that would be 19.3 feet using our right Riemann sum. Okay, so then the last part is your approximation in part C greater than or less than the actual answer? Give a reason for your answer. So let's see. If you take a first look at your first derivative, notice how your first derivative went from 5.7 to 4.0 to 2.0 to 1.7 to 0.6. The numbers are going down. So that means r prime is going down, it's decreasing, right? And we know that this whole thing is concaving down. So combine all that information, right? So part D says, we know it's concaving down, concave down, and r prime is decreasing. What does that give me? It gives me this graph looking like so, right? And now because that's a graph of concaving down and also r prime decreasing, we then plug in the idea that we have the right Riemann sum. So our RAM uses the right endpoint, right endpoint. So because of the curve and because of the way that we're using RAM, you can see that RAM is always going to be below our curve. So our right Riemann sum in this case, because of the way the curve is going to be an underestimate, right? So my approximation is less than the actual integral if we were able to calculate it. 0 to 12, r prime of t dt. And this is the answer. Concaving down, decreasing, and using RAM. Okay, that's it.